Our universe is a vast emptiness filled with celestial bodies, galaxies, and black holes of infinite complexity and diversity. The theory of general relativity explains how these massive structures interact within the four-dimensional fabric of spacetime and how they evolve. However, in the realm of quantum mechanics, a different perspective is offered regarding the microscopic behavior of matter and energy, as well as the methods of information preservation. This is where the holographic universe theory comes into play. The holographic universe theory posits that all information and events in the universe are stored on a two-dimensional surface, and the three-dimensional universe we perceive is actually a projection of this information on that surface. According to this theory, the volume of the universe can be fully described by the two-dimensional information on its boundary. This principle is similar to the way a hologram works, storing a three-dimensional image on a two-dimensional surface. The origins of the holographic universe theory trace back to physicists studying the properties of black holes in the early 1970s. Black holes are known as regions where the gravitational force is extremely concentrated, and any matter or information within these regions cannot escape once it crosses the event horizon. This phenomenon presents a problem known as the information loss paradox. While quantum mechanics predicts the conservation of information, black holes seem to lead to the loss of this information. Black holes are regions in spacetime from which nothing, not even light, can escape due to their intense gravitational pull. These astronomical objects typically form during the final stages of the life of a massive star, following a supernova explosion. At the center of a black hole lies a singularity, a point of infinite density and zero volume. Surrounding the singularity is the event horizon, a boundary beyond which nothing can escape. In the early 1970s, physicist Jacob Bekenstein proposed that the entropy of black holes is proportional to their surface area. Entropy is a measure of the disorder within a system, and the idea that black hole entropy is proportional to surface area provided clues about the information paradox. The information preservation paradox is a significant issue, particularly regarding the nature of black holes. For example, consider a book falling into a black hole. The information within the book becomes unobservable once it crosses the event horizon. According to the theory of general relativity, this information would be eternally trapped at the center of the black hole. However, from the perspective of quantum mechanics, information should not be lost and should always be retrievable. This paradox raises the question of how information is stored and preserved on the event horizon of a black hole. In 1974, Stephen Hawking discovered that black holes emit thermal radiation and evaporate, a phenomenon known as Hawking radiation, indicating that black holes could lose mass and eventually disappear. The work of Bekenstein and Hawking led to the formulation of the Bekenstein-Hawking equation, expressing black hole entropy. In 1993, Dutch theoretical physicist Gerard 't Hooft proposed a solution to this paradox. 't Hooft demonstrated that the entropy of black holes is measured at the event horizon, effectively a two-dimensional surface. The first step in 't Hooft's work was to understand the relationship between black hole entropy and information. Entropy measures the disorder of a thermodynamic system, and black hole entropy is a quantity measured at the event horizon. Stephen Hawking and Jacob Bekenstein discovered that the entropy of black holes is proportional to the surface area of the event horizon. This implies that the entropy of black holes is related to their two-dimensional surface area rather than their three-dimensional volumes. Building on this finding, Gerard 't Hooft proposed the idea that all physical information in the universe could be stored on a two-dimensional surface. The second step in developing the holographic principle involved using quantum field theory to calculate the information storage capacities of black holes. Quantum field theory, one of the fundamental theories of particle physics, suggests that all particles and interactions in the universe are defined through quantum fields. Gerard 't Hooft used this theory to examine how black holes store information on their event horizons and how this information is preserved during black hole evaporation. These calculations demonstrated that the entropy and information storage capacities of black holes are stored on the two-dimensional surface of the event horizon. To solidify the theoretical foundation of the holographic principle, 't Hooft mathematically formulated this principle. Mathematical modeling is an essential part of theoretical physics, ensuring that theories are testable and consistent. Gerard T. Hooft employed various mathematical tools to calculate the entropy and information storage capacities of black holes. These calculations showed that the information stored on the event horizon of black holes is not lost during black hole evaporation and is preserved on the two-dimensional surface of the universe. These mathematical formulations provided a strong theoretical basis for the holographic principle. By examining the microstates of black holes, Gerard T. Hooft further detailed the relationship between entropy and information storage capacities. Microstates represent all possible quantum states of a system, and entropy is a measure of the number of these microstates. T. Hooft also analyzed the microstates of black holes, explaining how information is stored on the two-dimensional surface of the event horizon and how this information is preserved during black hole evaporation. These analyses provided a more comprehensive and detailed explanation of the holographic principle. One of Gerard T. Hooft's final steps in developing the holographic principle was exploring its relationship with string theory. String theory is a theory in which the fundamental particles of the universe are described as one-dimensional strings. This theory yields significant results in areas such as quantum gravity and black hole physics. T. Hooft investigated how the holographic principle aligns with string theory and how these two theories could work together to resolve the information paradox of black holes. This integration provided new perspectives on understanding the fundamental nature of the universe. In 1995, American theoretical physicist Leonard Susskind further developed the holographic principle. Susskind argued that all the information in the universe could be stored on a two-dimensional surface and that the three-dimensional universe we perceive is a projection of this information. This idea had a significant impact, especially in the fields of string theory and quantum gravity. Susskind's work led to the acceptance of the holographic principle as a general principle and demonstrated that it could play a crucial role in understanding the fundamental nature of the physical universe. One of the most significant developments in the holographic universe theory came in 1997 when Argentine theoretical physicist Juan Meldacena proposed the anti-de Sitter/conformal field theory correspondence. Meldacena showed that a string theory formulated in a five-dimensional anti-de Sitter space is entirely equivalent to a four-dimensional conformal field theory. This duality was accepted as a robust mathematical foundation for the holographic principle and helped solve many problems related to quantum gravity. This duality has opened up new research areas in many branches of theoretical physics and has led to the holographic principle being accepted as a universal principle. According to the holographic universe theory, instead of a three-dimensional space of the universe, all the information in any region of the universe can be encoded on a two-dimensional surface at the boundaries of that region. This implies that the universe can be defined in a lower dimensional form rather than as a three-dimensional volume. The holographic universe theory differs from the traditionally considered three-dimensional spacetime structure, as it suggests that the fundamental physical information of the universe can be stored on a two-dimensional surface. This approach means that information can be compressed more efficiently and that complex structures of the universe can be defined in a simpler form. While in a normal universe information is typically thought to be spread out in three-dimensional volumes, the holographic universe approach proposes that this information can be concentrated in a lower dimensional and limited area. The holographic principle is a deeply studied topic in disciplines such as quantum gravity and quantum information theory, which are important areas of modern physics. It plays a significant role in bridging the gap between general relativity and quantum mechanics theories. By addressing issues such as the entropy and information storage capacity of black holes, it has introduced new perspectives on fundamental problems like information preservation in quantum gravity theories. At the same time, it demonstrates how we can explain the effects of gravity in a way consistent with string theory. Don't forget to subscribe for new documentaries and more scientific content.